Okay, in this video we're going to talk about levers. A remark attributed to Archimedes is, "Give me a place to stand, and with a lever I will move the whole world." This also applies to torque. See how Archimedes has set the earth up so it is closer to the fulcrum, reducing the amount of force he needed to exert to move it. Of course, this is just an illustration. Okay, so here is a screwdriver handle. Here you see it, A and B. We have it from the top view. We're looking at the handle, and the shank, that's the long thin part that connects the handle to the tip, which contacts the screw of the screwdriver, goes into the page. Assuming a constant force applied to both screwdrivers, which one would turn the screw easier? Would a longer shank help? The force is applied perpendicular to the radius of the handle. The forces are the same. Since torque is equal to Rf sine theta, the greater the radius, the greater the torque. Hence, the greater the angular acceleration. So in this case, screwdriver A is more effective. The length of the shank does not matter, assuming it is a perfectly rigid body and does not bend or deform under the force. Which scenarios regarding torque are true? Select two. Torque is measured in Newton meters. Torque is measured in joules. Torque is a vector. Torque is the same as work and energy. Go ahead and pause the video if you need to. Okay, the correct answers are A and C. Okay, so the correct answer is A and C. Torque is a vector, and again, we use the units of Newton meters, not joules. Okay, torque is the rotational analog to force. Newton's second law states that F equals ma. Time to derive the angular version of this law. Newton's second law has been applied assuming it is dealing with point particles that don't rotate. We now have an extended rigid body. But let's start with the force on one small piece of the rigid body as it's rotating. We know that F is equal to ma, and if we replace A, the tangential acceleration, with the rotational acceleration equivalent, we end up with the force is equal to mr alpha, because A is equal to r alpha. Assume that the force is applied perpendicular to the line connecting the axis of rotation with the force, and that means that sine theta equals 1. So now we know that torque is equal to Rf, and again remember that the radius and the force must be perpendicular to one another. We substitute in our new equation for force, which is not ma, but mr alpha. Substituting that in, we end up with mr squared alpha. Now if we sum up all the little pieces of the rigid body, we end up with the sum of the torque is equal to the sum of the masses times r squared times the angular acceleration. Why was the angular acceleration factored out of the summation? It's because alpha is constant for all the points on the rigid body. So now we're going to talk about moment of inertia. This looks very similar to Newton's second law in translational motion. The sum of the force has been replaced by the sum of the torque, and A has been replaced by alpha. But what about M? M has been replaced by the summation of mass times the radius squared, or the distance from the pivot point to the mass's location squared. This is a new concept. This is the rotational mass, which we've already covered in lab. We're going to call that the moment of inertia, and again we use I. So for a single point rigid body, the moment of inertia of all those little tiny bodies in this whole system is equal to the sum of the mass times the radius squared. Now again, this is not the radius of the small object. This is the distance from that small point object to the pivot point. The mass of a given rigid body is always constant. Can the same be said for the moment of inertia? No. The moment of inertia depends on the configuration of the rigid body, as you found out from the lab. Its axis of rotation location also will determine what the moment of inertia will be. So here's Newton's second law for rotational motion. The sum of the torque is equal to I alpha, where I, the moment of inertia, is equal to m1r1 squared plus m2r2 squared plus m3r3 squared, and so on. If more of the little pieces of the rotating object are located further away from the axis of rotation, then its moment of inertia will be greater than an object of the same mass where more of the mass is concentrated near the axis of rotation. Here are various moment of inertia for common objects. So here you can see, again, the hoop, which is mr squared, the hollow cylinder, which we also used, which is 1/2 m times r1 squared plus r2 squared, the solid cylinder, which is just 1/2 mr squared. Notice here we have a rectangular plate rotating about its center. That is 1/12 m times a squared plus b squared. A long thin rod rotating about its center is 1/12 ml squared. Notice if the rod is rotated by its end and not through the middle, it's 1/3 ml squared. If we have a solid sphere rotating about its center, it's 2/5 mr squared. If it's a thin spherical shell, then it's 2/3 mr squared. Just as mass is defined as the resistance of an object to accelerate due to an applied force, the moment of inertia is a measure of an object's resistance to angular acceleration due to an applied torque. The greater the moment of inertia of an object, the less it will be likely to accelerate due to an applied torque. The same torque is applied to a solid cylinder and a rectangular plate. Which object will have a greater angular acceleration? You can go back to the previous slide and look at it to find the moment of inertia for those objects. Since the rectangular plate has a smaller moment of inertia, it will have a greater angular acceleration. The angular acceleration can be different for the same object if a different axis of rotation is chosen. So if you want to rotate from rest a long thin rod, where should you hold the rod to make it easiest to rotate? A child rolls a 0.02 kilogram hoop with an angular acceleration of 10 radians per second squared. Actually, let me go ahead and answer that question for you. I thought that maybe it's down here. Here it is. Sorry. Okay, you have to hold it in the middle. By rotating it about that axis of rotation, the rod has a smaller moment of inertia. So for a given torque, it will have a greater angular acceleration. It's going to be easier to rotate if it's held at its center. A child rolls a 0.02 kilogram hoop with an angular acceleration of 10 radians per second squared. If the hoop has a radius of 1 meter, what is the net torque on the hoop? Go ahead and pause your video now. Okay, so let's see if you have the right answer. The correct answer is A. Okay, we take the I alpha, we find the moment of inertia for a hoop. You then multiply by our mr squared for the hoop, and then you go ahead and find the angular acceleration, or you have the angular acceleration, so then you multiply I times alpha. A construction worker spins a square sheet of metal of mass 0.040 kilograms with an angular acceleration of 10.0 radians per second squared on a vertical spindle. What are the dimensions of the sheet if the net torque on the sheet is 100.0 Newton meters? Go ahead and pause now. Actually, I'm going to show you the question because I know you can't see it on your sheet. Okay, the correct answer is C, 39 meters by 39 meters. Okay, in the next video, we're going to talk about rotational kinetic energy.